All right. In section 4.5, looking at planar graphs and Euler's theorems, not Euler's theorem. So we've got some vocabulary here: cycle, simple circuit. We circle back to some vocabulary from previous sections as far as like cycle versus simple circuit, and so that'll be kind of a key thing to look back and make sure that those are written in your notes to kind of help. All right. So starting us off here, definition. A graph is planar if it can be drawn in the plane so that no edges cross. A pair of edges cross with the line segments or arc represent them intersect at some point. All right. Such as a drawing is called a planar representation. So if something is planar, it's called a planar representation of the graph. So example one, we have a K4, so 4 vertices. And the question is figure 2a planar? And the answer is the way that it's drawn, it is not planar because it has an intersection. However, is that K4 can also be represented in figure 2b. And so in this representation, no pairs of edges intersect, so therefore K4 is planar. Our example 2. Kind of the same idea. So figure 3a, we sketch a cube with 12 edges, 8 vertices. We think of this as sketched as being a graph, and this graph planar? Well, we have intersections, so even though this is three-dimensional, and when we think about planar, we're thinking about being on one plane. So in this case right here, the way this cube is drawn, the face A, B, D, C would be one plane, and then E, F, G, H, or HG would be in another plane. But in this case right here, that means that it's not planar because it's not all in one plane. If it was smashed and it was one-dimensional or two-dimensional instead of three-dimensional, then it wouldn't be planar. However, we can redraw this graph to represent this situation right here. So therefore, this is planar because no pair of edges cross. All right, so a new definition is a cycle. So previously up to this point, we had a circuit, which begins and ends at the same vertex. We have a simple path where no edge is repeated, and we have a simple circuit where no edge is repeated. I think simple path is no vertex is repeated, but no edges repeated is a simple circuit. So a cycle is a simple circuit in which only one vertex, the initial vertex, is repeated, and is repeated exactly once. So that whole idea is that it begins and ends. So a cycle begins and ends at the same vertex. I'm just going to write that down. So it begins and ends at the same vertex. And on top of that, no edge is repeated. So that's kind of our key thing about this new definition here. So in figure 4, we have the cycle A, B, C, A. And so that is a cycle because of the fact that it's a simple circuit. It starts and ends at A, and no edges are repeated. However, let's grab the eraser. And if we do this time, but we go from A to C to B, I need to do a better job of reading, huh? From B to E to D to B to A is a simple circuit, but it's not a cycle because the vertex B is repeated. And so it would not be a cycle in that particular case, so in figure 4. Oops, sorry about that. Okay, so then we get on to Euler's theorem for planar graphs. So we're not going to prove this theorem, but basically Euler's theorem for planar graphs. In a planar representation of a connected planar graph, the relationship among R, which is your regions, the number of regions, V, the vertices, and E, the edges, is equal to this little formula here. So if we wanted to verify Euler's theorem for a planar graph in figure 5, we would start this guy off and we would say to ourselves, okay, well, let's see what we have. So let's see, so regions, and then vertices and edges. So vertices and edges we're getting pretty comfortable with. So vertices 1, 2, 3, 4. So there's 4 vertices. There are 1, 2, 3, 4, 5 edges. And I'm looking down here, it says 6. What am I miscounting? Oh, right there. So 1, 2, 3, 4, 5, 6. Sorry about that. So we have 6 edges. And in this particular case, we have 4 regions. So what happens here is we have region A, region B, region C, and then we have this region D, which is like unbounded. It's outside. And so there's going to be 4 regions on this guy. 4 regions. So to verify that Euler's theorem for planar graphs holds, that this is actually a planar graph, we can go ahead and plug this in, and we can say, all right, so 4 take away 6 plus 2 or plus 4 is equal to 2, so check. According to the theorem, this would be a planar graph because of the relationship between the regions, the vertices, and the edges. All right, next one. So we take a look at this guy, same thing, it's just another example. So in this particular case, we have vertices, we have edges, and we have regions. So vertices, we have 1, 2, 3, 4, 5, 6, 7, 8. Edges, we have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And for regions, we have 6. So we have 1, 2, 3, 4, 5, and then we have the region just outside of the shape that's unbounded, and that gives us 6. We plug that into our little relationship and check. So therefore, this would be a planar graph because the relationship meets the requirements. All right, that wraps it up for this section. Pretty straightforward, just kind of introducing the basic idea of what a planar graph is and how we can verify.